Welcome to the Electromagnetic Works Video Tutorial Series. This series is a collection of videos that will show you firsthand how accurately and how quickly you can get designs analyzed and optimized inside SolidWorks. This video will show you how to use our electromechanical simulation package, EMS, to simulate a three-phase transformer inside SolidWorks. In this tutorial, we will cover the AC magnetic simulation module. Before a simulation can be started, the CAD model of the transformer must be built or imported into SolidWorks. Our starting point will be a readily built CAD model, which will simply be loaded and analyzed. The model is the entire transformer assembly, including a steel core, 3 coils surrounding the bars of the core, and 3 coils surrounding those previously mentioned coils. Notice that there is another set of parts which represent the air. One part represents the air within the coil. Another is the air directly around the coil and in contact with the core. Fields can be strong there. Therefore, it is essential to add them in order to analyze the fields close to the bodies. They reflect the coupling between the transformer's parts. The outer air is an enclosure volume. This part should be made sufficiently large to ensure that fields are small enough at the far edge. To launch a new study, move to the EMS tab and right-click on the assembly icon, then select Study. An AC magnetic study is needed. Specify the input frequency to be 60 Hz, and select the inductance and thermal computations. Once the study is launched, the preprocessing inputs must be specified. The first of these inputs is the set of materials. The materials can be chosen from the EMS material library or from a user-created material. EMS can provide both linear and non-linear materials, as well as magnetic materials. The coils are all made of copper, which is found in the non-magnetic material folder. For any other copper body, you can apply a material from scratch again, or you can copy the material properties by dragging and dropping from a previously assigned body. Another way is to select a large set of components and apply the material to all of them. For the air parts, air will be selected from the material library. Finally, the core will have a material applied to it. We will choose mild steel. This is found in the ferromagnetic folder. When all bodies have been assigned a material, a blue checkmark will appear on the solids icon. The next step is to apply loads and restraints. From the set of thermal boundary conditions, we will choose convection. We will apply convection on all of the faces from the front, from the back, as well as the top, the bottom, and the sides, for both the core and the coils. We can also apply convection properties such as the convection coefficient and the ambient temperature. After loads and restraints, we apply the coils. There are 2 types of coils available: solid coils or wound coils, which have multiple turns. To select the faces inside a full model, apply a section view in the SolidWorks viewer. When applying the coil, you must specify the direction by selecting the body of the coil, as well as the faces of entry of the current and exit. In half or quarter problem models, the current enters one face and exits from another. But in full models, such as this one, they are the same. Then set the coil's current properties. In wound coils, specify the number of turns in the coil, then the magnitude and phase of the current. The current flows in a counterclockwise direction. Therefore, in all coils, the face of entry is in the right, and it is the same as the exit phase. For all inner coils, 2000 turns are present, with a magnitude of 100 amps. The phase of the current for the rightmost coil is 0 degrees. In the central coil, while sharing most other properties, it has a phase of 120 degrees. For the inner coil on the left, while it shares the number of turns, the direction of the current, and the amplitude, its phase is 240 degrees. All outer coils share the same properties. They all enter from the right counterclockwise and have 300 turns with 0 current. Finally, before running the analysis, the model must be meshed. Meshing is simple in EMS. By specifying the global size of the mesh and the tolerance for small spaces, the mesh can be created. Of course, there are some parts that are smaller than others. It would be a good idea to apply mesh controls on those bodies to make sure that the accuracy is not lost. For the coils in this model, all will have the same mesh control size. The element size will be 4 inches. The steel core will have another mesh control. The element size here will be 2 inches. For the air inside the coil, since the spaces are all very small, 6/10 of an inch will be applied. For the air immediately around the coil and the core, 8 inches will be the mesh size. Finally, all remaining bodies, in this case the far edge outer air, will obey the global mesh size. The global mesh size will be set to be 60 inches. And the tolerance will be 1/10 of an inch. This is done to accommodate the small gaps within the coil. After creating the mesh, you can review the size and make changes, and then you can choose to run the analysis.